Okay, so the final exam, which is on the last day of class, and we'll cover material from exams 2 and 4, mostly exam 4. The stuff from exam 3 is essentially, incorporated into the material for exam 4. So the stuff for exam 3 is included as well, although no questions specifically on that. So we will definitely have a problem like number 6 on exam 2. So that's finding the absolute maximum and absolute minimum of a function on some bounded domain. So number 6 here. So it seems like we didn't do so well on that problem as I would have liked. So definitely we want to cover that material on the final exam. Okay, so specifically, definitely take a look at this, see where you went wrong. Study problems like those, and let me know what questions you might have on that, and I can spend some time and help you out with it if you need. And last time, let's see, where did we leave off last time? We left off on number 90. Number 90. Oh, in exam 3, I'll announce for the date of it, but that will cover sections 5.1 through 5.6. I'll announce a date in the email after class. See how far we go today. See how far we get on the material today. So there's obviously less material there than what we did on the first couple exams. So we should get through that pretty quickly. Give us enough time to cover chapter 6. Okay, so last time we left off on number 90, so the next problem in section 5.2 is 94. And the question asks, find the average value of a function on a certain region. So let's talk a little bit about the average value of a function and what that means, and see how integration helps us take care of that. So let's review that quickly. So average value of a function. So for a one variable function, so in the xy plane, you've got some interval a to b, and you've got some function y equals f of x on that interval from a to b. So if you cut the interval up into subintervals as usual, right, so this is x1, x2, x3, x4, x5, x6, x7, like that. And then you take those, so forgetting about rectangles for the moment. And you take those values of the function, sort of evenly spaced width-wise along the curve. Y equals f of x. And then b is x8. So the average value of f of x on a less than or equal to x less than or equal to b. Well, it's reasonable to assume for a continuous function that the average value is approximately what? The sum of these n sample points, f, x, y. Right? I mean, that's what an average is, or a mean if you're in statistics, statistic lingo. So the average value of a function, 1 over n, times the sum of these n values of the function, nice and evenly spaced along the curve, width-wise, kind of along the curve there. Well, along the curve, evenly spaced width-wise. And certainly this average becomes more accurate to what you would think it would be as n gets larger. So as n tends towards infinity, right, this estimate of average value gets more and more accurate. Therefore, the average value of a function is not approximately equal to something, but is now actually equal to the limit as n goes to infinity of this quantity here. The limit as n goes to infinity of the average value for n points, evenly spaced on the x-axis. Okay, now if you let delta x, which is the width of these subintervals, delta x is equal to, well, what is that? It's b minus a over n, the length of the interval divided by the length of the interval from a to b divided by n to n equal subintervals. So if you take this quantity here now and you rewrite it as the limit as n goes to infinity of 1 over n times the sum I equals 1 to n f x I b minus a over b minus a. And that's, of course, equal to 1. So put the n over here and bring this b minus a out. So it's the limit as n goes to infinity, 1 over b minus a, the sum I equals 1 to n, f x I b minus a over n. So we took the n, brought it in here, because that's a constant with regard to this summation, and brought the b minus a out. But what's this right here, b minus a over n? What is this b minus a over n? What is that quantity? It's delta x. So it's the limit as n goes to infinity, 1 over b minus a, sum I equals 1 to n, f x I delta x. Now, by definition, right, the integral from a to b of f x dx is equal to what? What is the definition of the integral from a to b of f? What is that definition? I'm going to bring this constant outside. Well, let me just rewrite this one. By definition, this integral is equal to what? Right? Not the fundamental theorem of calculus, not f of b minus f of a, where capital F is an antiderivative of, of little f. Right? That's the fundamental theorem of calculus. It's not the definition of the integral. The definition of the integral is what? Well, it's the limit as n goes to infinity of that Riemann sum. The Riemann sum, y equals 1 to n, f x y delta x. Right? And that's exactly what we've got. That's exactly what we've got over here. So the average value of a function turns out to be 1 over b minus a times the integral from a to b fx dx. Pretty cool. Right? So instead of just being an area measurement, an integral is actually an average value measurement. So you just take the integral and then you divide by b minus a, which is what? Is the length of the interval. So this is the length of the interval a less than or equal to x less than or equal to b. The length or the measure of the integral, right, from b minus from a to b, and this is the integral of f of x over that interval. So it's the integral divided by the measurement of the interval. Integral divided by the measurement of the interval. The interval is the domain along which you are integrating your function. Right? So for 2-variable and 3-variable functions when we get there, so for a 2-variable function, z equals fx y, similar calculations yield that the average value of fxy on domain D, right, where D is, some domain in the two-dimensional plane, the average value of the function over that domain in the two-dimensional plane is 1 over, well, what's the measurement of D? How does one measure D? You measure an interval by measuring its length. Here, you measure D by taking its area. It's the area of D times the double integral over D of fxy dA. It's the same idea. I mean, I could go through those calculations. It's just, a little messier, explaining the whole thing, but it goes basically like that. And then when we get to triple integrals, it's the average value of a 3-variable function over some 3-dimensional domain, and it's 1 over the volume of D, the triple integral. For 3-variable function, we'll see that if you watch the video already for section 5.4. For a 3-variable function, average value of f, x, y, z over domain D is 1 over the volume of D, the triple integral over D, f, x, y, z, dv. Okay, so integration, not only calculates, a volume in the in the two variable case, and a mass in the three variable case from a density and mass calculation. It also calculates average value, where you just have some constant that you divide the integral by. So in number 94, so this is section 5.2, number 94, find the average value of fxy equal to sine y on this triangular region 0, 0, 0, 3, 3, 0. So this is 3, 0, 0, 3, and 0, 0. Like so. Okay, so, f of x, y equals sine y on this region D. Okay, well, first thing we need to do is to describe region D as either type 1 or type 2. So let's do it as type 1. So type 1 description for D. So let's draw it again. Right, here's the x-axis, here's the y-axis, here's that line. This is 3 on the x-axis, 3 on the y-axis. Okay, so what is the constant bounds for D, or for x on D here? What are the constant bounds there?
0 and 3.
0 to 3. So now, if you take a value for x between 0 and 3, the boundaries for x above and below are here and here. The boundaries for y, excuse me, above and below are here and here. Okay, so y is from the x-axis to this line. What is the equation of this line here? All right, the equation of this line is, well, it's x plus y equals 3. If you want to write that differently, it's y is equal to minus x plus 3. So slope -1, y-intercept 3. So y goes from where to where? Well, from here, from this straight line here to this slanted line up here. So the boundaries for y are where to where? Right. 0, that's the horizontal line, the x-axis, 2 minus x plus 3. Okay, so type 1 description for D. So the average value is 1 over the area of D, double integral over D, sine y dA. Well, what's the area of D? Well, it's just a triangle, so we know what that area is. It's 1/2 the base times the height. Right, so it's 9/2. Iterated integral, starting from the bottom to the top here, inside out, 0 to 3 minus x, 0 to 3, sine y, again bottom to top here, dy dx. So this is equal to 2/9. Antiderivative of sine y with respect to y is minus cosine y, from 0 to 3 minus x, and then dx. So it's 2/9 times the integral from 0 to 3. So cosine 3 minus x minus cosine 3 minus x plus cosine of 0, which is 1, dx. Cleaning up that expression, 2/9, integral from 0 to 3, 1 minus cosine 3 minus x dx. All right, antiderivative of 1 is x, and the antiderivative of cosine 3 minus x. Well, the antiderivative of cosine is sine. I mean, you really, have to use a u substitution here, right? Let u equal 3 minus x, and then du is the negative of dx. But we can skip that substitution. The antiderivative of cosine is sine, but then you've got this negative to deal with, so it's going to be negative sine. So plus sine 3 minus x from x equals 0 to x equals 3. So we get 2/9, and then at 3 plus sine of 0 minus 0 plus sine of 3. So this is 3, that's 0, so 3 minus sine of 3. So 2/9, 3 minus sine 3. And that's the final answer for that. This is not like the greatest example to try to reverse the order of integration, so we'll just leave it at that. All right. That's 94, 96. In the following exercises, change the order of integration and then evaluate the integral. So 0 to x plus 1, and then minus 1 to pi over 2. Or x plus 1. Sine y dy dx. So in order to reverse the order of integration, we need to look at what this region is. So this region, since we're doing dy dx, is a type 1 description of a region. So we need to turn that type 1 description into a type 2 description. So this region is 0 less than or equal to y less than or equal to x plus 1, and then minus 1 less than or equal to x less than or equal to pi over 2. Right, so this is the domain D, type 1. So in order to reverse it, we need to draw this and see what it looks like. So x goes from -1 to pi over 2. And then we've got the line from 0 to x plus 1. So x plus 1 and -1 is right here, and then it goes up to this point right there, which is going to be pi over 2 plus 1. So pi plus 2 over 2. Okay, so instead of describing it as a type 1 region, now let's describe it as a type 2 region. What are the boundaries for y? Well, the constant boundaries for y are from here to here. All right, so y is going from here to here. So we've got 0 less than or equal to y less than or equal to this point right here, pi plus 2 over 2, which is pi over 2 plus 1. And then for a specific value of y within that interval, we're going from here to here. The upper curve, or the right-hand curve, is this line, and the lower curve is this slanted line. So, sorry, for that particular value of y, the boundaries for x are as follows. X goes from here, from the slanted line, to this. Well, what's this right here? What's this upper bound for x? What's this upper bound for x? This line right here. That's x equal to
pi over 2.
Pi over 2. And what's the lower bound? Well, this is the line y equals x plus 1. Right, so if you solve for x, this is x equal to 1 minus y. Right, or no, sorry, y minus 1. Right, x equal to y minus 1. Yeah, you subtract 1 on this side. So the lower bound for x is y minus 1. So this is a type 2 description of that region. So now we can rewrite the integral in terms of that type 2 description. So that is equal to pi over 2 to y minus 1, or sorry, y minus 1 to pi over 2, and then 0 to pi plus 2 over 2. Sine y dy, or sorry, dx dy. Right, so, all right, well, because there is, so now we take the antiderivative with regard to x. Well, for the antiderivative with regard to x, there's no x's in this, so that's just a constant. So it's just the constant times the length of the interval, pi over 2 minus y minus 1. Right, remember, the integral from a to b of k dx is just equal to k times b minus a. All right, so just a little shortcut there to help out. So this is y minus 1 pi over 2 minus y plus 1 times sine y dy. Okay, well, now let us do some distribution here. So integral from 0 to pi plus 2 over 2. So I got pi over 2 plus 1. So this is pi plus 2 over 2. And that's just a constant, right? Sine y minus y sine y dy. Well, I guess we don't really need to do that. Let's not do that. Let's just do our integration by parts. This is a polynomial in terms of y. Right? It's just y minus, minus y plus some constant. And this is sine y. So in the order of choosing the parts, u and dv, you take the polynomial first and the trig function second. So sine y dy, and then u is pi plus 2 over 2 minus y. So du is just minus dy, and that's just a constant there. And v, antiderivative of sine y, minus cosine y. So the integral is u times v. So it's y minus pi plus 2 over 2 positive cosine y, distributing the minus sign through here, right? Minus pi plus 2 over 2 minus y just reverses that. Evaluated from 0 to pi plus 2 over 2 minus v du. Antiderivative v du. So I have minus, minus, minus. So that stays minus. Cosine y dy. Okay, so evaluating this, so at pi plus 2 over 2, we get 0. Minus, at 0, so at 0, this becomes minus pi plus 2 over 2 cosine 0. Minus, antiderivative cosine y is sine y. So we get, this is just positive pi plus 2 over 2. And this is minus sine pi plus 2 over 2 minus sine of 0, which is 0. So we just get pi plus 2 over 2 minus sine pi plus 2 over 2, whatever that is. Pi over 2, right. Let's do the integration in the other order, in the original order, and see that we get the same answer. In the original order, and see that we get the same answer. So the original looks like this. So antiderivative of sine y with regard to y is just minus cosine y from y equals 0 to y equals x plus 1 dx. So we have the integral from minus 1 to pi over 2. So it's minus cosine x plus 1 minus cosine of 0. So, no, it becomes plus. Minus cosine of 0 is plus. So that becomes 1 minus cosine x plus 1. So antiderivative is x minus, antiderivative cosine is just sine, x plus 1, from minus 1 to pi over 2. So this becomes pi over 2 minus sine pi plus 2 over 2. And then at minus 1 plus sine of 2. Ooh. So we get pi over 2 plus 1, which is pi plus 2 over 2. Pi over 2 plus 1. Minus sine pi plus 2 over 2 minus sine 2. Oh, this is supposed to be a minus 1 minus. That's supposed to be a minus. So that becomes a plus. Well, that is different than what we got now, isn't it? So we've got this extra sine of 2. Let's see if we can't track that down. That error. So y minus 1 less than x less than pi over 2, minus 1 to pi over 2, and then this is y equals x plus 1, so that's x equals y minus 1, so y minus 1 is less than x less than pi over 2, and 0 is less than y is less than pi plus 2 over 2. So y minus 1 to pi over 2, 0 to pi plus 2 over 2. So antiderivative of sine y, and the difference. So pi over 2 minus y plus 1 is pi plus 2 over 2. Pi over 2 plus 1, pi plus 2 over 2. So u is pi plus 2 over 2 minus y. So du is minus dy. dv is sine y, so v is minus cosine y. So u times v from 0 to pi plus 2 over 2 minus v du, antiderivative, 0 to pi plus 2 over 2. All right. So at pi plus 2 over 2, this is 0, minus 0 minus pi plus 2 over 2 cosine 0, which is 1. Antiderivative cosine is sine pi plus... Oh, I see what I did. No, y goes from 0. No, that's right. So sine pi plus 2 over 2 minus sine of 0, which is 0. That seems right. What about here? So 1 minus cosine x plus 1. So minus cosine x plus 1 plus cosine of 0. Sine of x plus 1, x is negative 1. So it's not sine of 2, it's sine of 0, right? So it's pi over 2 minus sine pi plus 2 over 2 minus negative 1. This is negative 1 minus sine of 0, not sine of 2. Sine of 0. So same answer as before, see? All right. So that was 96. 98. Same thing. So we've got this double integral here, integral from minus 1 to 0, and then minus root y plus 1 to root y plus 1, y squared dx dy. So we've got a type 2 integral. So 98, integral from minus 1 to 0, minus root y plus 1 to root y plus 1, y squared dx dy. So this is a type 2 interval, so minus 1 less than or equal to y, less than or equal to 0, and then minus root y plus 1 less than or equal to x, less than or equal to root y plus 1. That's type 2. So let's draw the region. So y goes from minus 1 to 0. So this is y right here, minus 1 to 0. The square root of y plus 1, that's the square root of y, square root of y shifted to the left 1, so that's square root y plus 1. And then the negative of square root y plus 1 is right here. I think or no, I'm sorry. No, that's square root x plus 1. Square root y is right here. Square root y plus 1, you shift that guy down. So this is x equals square root y plus 1. This is x equal negative the square root y plus 1. Right, square root y is right here, and we're shifting it down. So this is 1 and negative 1, and y goes from 0 to negative 1, and then x goes from here to here. So we're talking about this region. Right, so this is the region or domain that we're talking about. Well, what is a type 1 description? Well, what are the bounds for x? Constant bounds for x. what's the range for x here? And what's the extreme left and right for x on this interval?
-1 to 1.
Yeah, -1 is less than or equal to x is less than or equal to 1 right here. All right, and then given x in that interval there, y goes from, this curve to 0. So the upper bound for y is the x-axis. That's just 0. And then the lower bound for y are these square root things. Well, what is this? I mean, this is x equals y, square root y plus 1. So this is x squared equals y plus 1. So this is y equals x squared minus 1. Right? Y equals x squared minus 1 subsumes both of these curves, right? And y equals x squared minus 1, of course, doesn't have an inverse function because it's not 1 to 1, but it's kind of got like an inverse function in two parts, right? The positive square root y plus 1 and the negative square root y plus 1. Right? So the lower bound for y is just x squared minus 1. So this should make an easier calculation than this original one here. So this is equal to double integral from x squared minus 1 to 0, and then from minus 1 to 1, y squared dy dx. Antiderivative with regard to y is 1/3 y to the third from y equals x squared minus 1 to y equals 0 dx. So this turns out to be the integral from -1 to 1. So at 0, of course, that's 0, minus, I'm going to pull the 1/3 out front here, x squared minus 1 to the third. So if you know how to multiply this out quickly, so I'm gonna bring the negative sign out front. So negative 1/3 x squared minus 1 to the third. So that's x squared to the third is x to the 6 minus 3x squared times 1 plus 3x squared times 1 squared minus 1. All right, that's using Pascal's triangle. So what we get here is minus 1/3 antiderivative 1/7 x to the 7th minus x to the 3/5 x to the 5th plus x to the third minus x, all from x equals -1 to x equals 1. So at 1, what is this? This is 1/7 minus 3/5 plus 1 minus 1. Minus, at -1, these are all the same value, except they're negated because they're all odd powers of x, right? -1 to the 7th is -1. -5 to the -1 to the 5th is -1. -1 to the third is -1, and x equal -1 is just -1 again. So what it actually turns out to be is double becomes plus. So then it's the negative of this, but it's subtracted, so it becomes plus. So that's 1/7 minus 3/5 plus 1 minus 1, and those go away, of course. So we've got minus 1/3, so 2/3. So common denominator is 35. So 5 minus 21 over 35, so 16. So 32 over 105. Okay. What would it be like to calculate this integral? Yeah, calculating this integral this way, that's got some problems. Does anyone see it? What the problem is with that? Let me show you. So notice that the original integral is difficult to calculate. This one wasn't bad. It's just polynomials. But let's look at this one. Let's do the first iteration, and then you see, how nasty it is. So this is dx, and then that's there's no x's. It's just y squared. So it's just the length here. So it's twice that. So this becomes integral from minus 1 to 0, 2y squared square root y plus 1 dy. How do you do the antiderivative of that? It's not that bad, actually. It's not too hateful. Not too hateful. Does anyone know the trick? So let's calculate the original. Iterated integral. Anyone see the trick to that one? It's a u substitution. Right, so the u substitution is let u equal y plus 1. So y equals u minus 1. And for y equal to 0, u is equal to 1. And for y equal to minus 1, this is for u equal to 0. So this becomes, and then dy is du, of course, because that's just a simple linear function there, linear substitution. So du equals dy, y equals u minus 1. So this becomes the integral from u equals 0 to u equals 1 to u minus 1 squared square root u. See? Now that becomes u to the 1/2, and I can distribute it. So I took the sum out of the square root, and I pushed it over here. And that works out fine. So this becomes integral from 0 to 1. I'll put the 2 out here. U squared minus 2u plus 1 u to the 1/2 du. So this is 2 integral from 0 to 1 u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. Right, so this is fine. It's all just a rational, rational exponents. So we know how to do the positive rational exponents. So antiderivative is no problem. Just use the reverse of the power rule. So 5 halves plus 1 is 7 halves. So it's 2/7 u to the 7 halves minus 5 halves. So that's 4/5 u to the 5 halves plus 3 halves. So it's 2/3 u to the 3 halves from 0 to 1. So this becomes equal to 2 times 2/7 minus 4/5 plus 2/3. The common denominator, 7, 5, and 3, is just their product, which is 105. So it's 2 times, so 15 times 2 is 30. 4 times 21 is 81. Yeah, and then 2 times 35 is 70. So this is equal to 100 minus 81 is 19. Wait, oops. What happened here? 21 times 4, 84. Right? 21 times 4 is 84. 16, not 19. So that's 32 over 105. Right? Same answer. Nice, nice. Okay. Next, 102. Find the volume of the solid under the surface and above the region. You know, that's just a double integral, right? The solid under this surface and above this region, that's just the double integral, right? So for 102, right, so the volume of solid under y equals, or z equals fxy, and above d, right, so here's x and here's y, here's the d. So as long as fxy is positive, then this like makes sense. Otherwise, I mean, it doesn't quite. So you have some surface here. Right, z equals fxy. So you've got that surface, and you're measuring the volume under the surface and above that region. So that's just the double integral. That's the classic definition of that thing. Right. So all right. So let's look at what we've got here. So we have the surface z equals 2x plus y squared. So in this problem, z equals 2x plus y squared, and d is the region bounded by y equals x to the fifth and y equals x. So y equals x to the fifth right? I mean, it sort of looks like a parabola. It's just a little more flattened out on the bottom there. And on the other side, it's the same thing reflected through the origin. So you flip horizontally, and then you flip vertically. That's it right there. All right, and then the line y equals x is this. Now, where do these guys meet? Where do these guys meet? All right, they meet where x to the fifth equals x. So where x times x to the fourth minus 1 equals 0, so x is equal to 0, 1, and minus 1. Right, so this is the point 1, 1. That's the origin, of course, and that's the point negative 1, negative 1. Can we describe this as type 1 or type 2? No, because, here, right, this curve is above the line, and here this curve is below the line. So you have to do two regions. Right? You have to do this in two regions. So the region, right, or the domain, so D is equal to domain 1 union domain 2. So this is domain 1, this is domain 2. So where domain 1 is minus 1 less than or equal to x less than or equal to 0, and then x less than or equal to y less than or equal to x to the fifth. And then domain 2 is 0 less than or equal to x less than or equal to 1, x to the fifth less than or equal to y less than or equal to x. Right? Because the line is above the curve over here, and the line is below the curve over here. So to do the double integral, you gotta split it up into two subintegrals. And probably, well, I don't know, I think maybe the answer would be the same over each subinterval. Let's see. So over d1, so the double integral over d1, 2x plus y squared dA is, so x to the fifth minus 1 to 0, 2x plus y squared dy dx. So this is equal to the integral from minus 1 to 0, antiderivative with regard to y, so x to the fifth minus x. Right, so this is a constant with regard to y, 2x. So it's 2x times x to the fifth minus x. And then this is 1/3 y to the third from y equals x to y equals x to the fifth. That's nasty. Dx. Oh, no, it's not bad because it's just a monomial. Just monomials here. So this is equal to the integral from minus 1 to 0, 2x times x to the fifth minus x plus 1/3, so x to the 15th minus x to the third. So we've got, no, minus 1 to 0. Integral from minus 1 to 0, so I got 1/3 x to the 15th. 1/3 x to the 15th, and then 2x to the 6th, and then minus 1/3 x to the third, minus 2x squared dx. Well, let's see. So antiderivative is 3 times 16 is 48. Yeah. So 1 over 48 x to the 16th plus 2 over 7 x to the 7th minus 1 over 12 x to the 4th minus 2/3 x to the 3rd from minus 1 to 0. So it's minus 1 over 48 minus 2 over 7 minus 1 over 12 plus 2 over 3. Because these guys are odd, these two are even. So plus 1 over 48 minus 1 over 12 minus 2 over 7 plus 2 over 3. Which is equal to hello. I've got it right. There we go. 1 over 48 minus 2 over 7 minus 1 over 12 plus 2/3. (107 over 336). Well, minus 1 over 7 over 336. Let's double check that integral. So 1/3 x to the 15th that's not 2/7 x to the 7th minus 1/3 x to the 3rd minus 2/3 1/12 x to the 4th minus 2/3 x to the 3rd minus 1 to 0. So you get minus 107 over 336. All right, so then over D1, yeah, I don't think they're not going to be the same. I thought maybe it might be the same over D1 and D2 because it seemed kind of symmetric, but the one over D2 is going to be positive, right? Because D2, these are positive values of x and y. And the function, the positive values of x and y, is positive, so the integral will be a positive, not negative. So this is not correct, that they would be the same. So over D2, so this is 0 to 1, x to the 5th, x. So 2x times x minus x to the 5th plus 1/3 y to the 3rd from y equals x to the 5th to y equals x dx. So integral from 0 to 1, so this is 2x squared minus 2x to the 6th plus 1/3 x to the 3rd minus 1/3 x to the 15th. So this is equal to 2/3 x to the 3rd minus 2/7 x to the 7th plus 1/12 x to the 12th minus 1 over 48 x to the 16th from 0 to 1. So this is 2/3 minus 2/7 plus 1/12 minus 1 over 48. So plus 2/3. So all right, that was a negative sign out there. Right. Because at 0, this is 0. So it's plus 2/3 minus 2/7 plus 2/3 minus 2/7 plus 1/12 minus 1 over 48. plus 112 minus 148. 149 over 336. So, therefore, the double integral over d, what was it again? 2x plus y squared dA is equal to so minus 107 plus 149. So 49 minus 7 is 42. That fraction, I'm sure. I'm sure it's so 42 divided by 1/8. Okay, so so that's how that problem goes. The final problem in this section, number 108, find the volume of the solid situated in the first octant, determined by the planes z equals 2, z equals 0, x plus y equals 1, x equals 0, y equals 1. Z equals 0, x plus y equals 1. So we need to draw this guy. So z equal to, so in the first octant, z equal to 0 is just the xy plane. So x plus y equal to 1 is this plane here. So this is z equal to 0, this is z equal to 2. And this is the plane right here. X plus y equals 1. And then z equals 0, z equals 2, x plus y equals 1, x equals 0, x equals 0. Well, this is all messed up. X equals 0 is the YZ plane. Oh, y equals 0 and y equals 0. So in the first octant, x equals 0 and y equal to 0. That's x equal to 0. That is the YZ plane. And y equals 0. That is the XZ plane. So this is the solid right here. So this is the plane x plus y equals 1. All right, so, well, what is the volume of this thing? I mean, it's just this triangular prism. What's this point and this point here? All right, it's just x plus y equals 1, so that's at 1 on the x-axis, 1 on the y-axis. All right, so the volume of this thing, so the volume of any cylindrical type construction like that is equal to the area of the base times the height. So this is the area of the base is just 1/2 1 times 1 times the height, which is 2. So it's just 1, the area of this thing. But if you want, you can calculate this. You can calculate this as a double integral. I mean, we don't have to. We know what the answer is. As a double integral, right? Measuring the volume of the solid under the function. Under what function? Z equal to what? Like under the function z equal to something, and then above what region in the plane? What's the upper function for z bounding this solid? It's just z equal to z equal to 2. Under z equal to 2 and above d equal to the bottom of this thing in the xy plane, which is just this triangle here. Right. So this is 1 on the x-axis, 1 on the y-axis, so this line is x plus y equals 1. Right, which is the same as y equals 1 minus x. So the description of this region, type 1 description, is 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1 minus x. So the volume is the double integral over d of 2 dA. Alright, so this is 2, bring the 2 outside, times the double integral from 0 to 1 minus x, from 0 to 1, dy dx. I'll leave the 2 over here. Alright, so this is integral from 0 to 1. Well, 2 has no y's in it, it's just a constant. So it's 2 times the difference of this here, so it's 2 times 1 minus x dx. So the antiderivative of that is 2x minus x squared from 0 to 1. So that's 2 minus 1 is 1. Yeah, same answer. Is there any other problem like that that's instructive? So that was 108. X plus 2y equals 1. It's the same kind of thing. It's another sort of zonotope. Just a simple polytope there. If z is equal to 4 is the top, and they just slanted this plane a little bit. Instead of x plus y is 1, it's x plus 2y is 1. Same deal there. Same dealio. 110, x plus y equals 1, x minus y equals 1. The same kind of, these are really that instructive here. These can all be done by calculating the area of the base times the height. In all cases. You're dealing with, well, not necessarily right triangles, but they're triangles that are lined up with the x and y axis in a nice way so that you can measure the base and the height. So nothing too instructive in these problems here. All right, the Relu triangle. Ooh, what's this thing? Balloons of Alhazen. Balloons of Alhazen. Huh. All right, let's move on to 5.3. Oh, well, it's 8 o'clock. Why don't we take 5 minutes? So 7:56. Let's come back at like 8:02. All right. So let's take a few minutes break and we'll be back. We are back. So section 5.3, number 122. So express the region D in polar coordinates. So we've got D is the region of the disk of radius 2 centered at the origin that lies in the first quadrant. So quarter disk of radius 2. All right, so this is the region D here. So as a polar rectangle with just constant bounds for r and theta, well, it's just the radius goes from 0 to 2, and the theta goes from 0 to pi over 2. Right? So when you're doing an integral over a circular type region, or these polar rectangle type regions, describing the regions using polar coordinates rather than rectangular coordinates makes things a lot simpler often. So that's 122. 126. So we have x squared plus y squared less than or equal to 4x. So the region defined by this. So, well, this is definitely a type of circle, right? Moving the 4x over here and then completing the square. Do you remember that? Take the 4, divide by 2, and you get 2, and square it, and then you add that to both sides. So add 4 to both sides. So this becomes x minus 2 squared plus y squared less than or equal to 4. So this is the disk, the circle of radius 2, well, the disk, the whole thing, of radius 2 centered at the point 2, 0. So this is 2 on the x-axis, and then we're talking about the circle here of radius 2. So what is a function r equals f of theta that gives you this? All right, does anybody know what function r equals f of theta gives that to you? Right, well, now the boundary of this, so the boundary of this region, x squared plus y squared equal to 4x, this gives you r squared is equal to 4r cosine theta. So r is equal to 4 cosine theta. So this is r equals f of theta. So as theta goes from 0 to 2 pi, as theta goes from 0 to 2 pi, you're getting r values that put you inside here. So from 0 to pi over 2, you go here, and then from pi over 2 to pi, well, the r values are negative, so they're going from 0 out to negative 4. Of course, this is 4 on the x-axis here, right? So the boundary of that circle is described by r equals 4 cosine theta. And these red lines are the r values that go along with theta. So if we just want the inside of that circle, right, how can we describe it in terms of a polar region? So now the r is no longer constant, right? Well, the theta values are just going from 0 to pi. They're just going from 0 to pi. So at 0, we're here, like we're out to 4. And then as you work your way up to pi over 2, cosine theta is going from, well, 4 cosine theta is going from 4 down to 0. So pi over 2, theta equal to pi over 2, r is equal to 0, puts you at the origin. And then as you go a little bit past pi over 2, the r values are negative. They're going from 0 out to negative 4. So the angle, the point 4 comma, pi comma negative 4 is over here. So pi 4 is here, or r 4 pi, excuse me, 4 comma pi is here. So negative 4 pi is over there. Right, so from 0 to pi, you're tracing out the whole circle. Right, so from 0 to pi over 2, the r's are going like this. And from pi over 2 to pi, the r's are going like that, right? So what gives you the inside of that? So r is between what and what? Right? R equal to 4 cosine theta puts you on the boundary of the circle. So what puts you inside the circle? Hello? Did I turn my mic on? I did. Right, those red lines are the r's. So the full red line gets you out to the circle. To keep you inside the circle, r should go from where to where? Right, 0 to 4 cosine theta. Right, so theta values from 0 to pi, and r values from 0 to 4 cosine theta, right? I mean, 4 cosine theta at 0 gets you all the way out here, but less than 0 gets you anything along that. Right, and then for like pi over 6, right, 4 cosine theta gets you over here, but anything less than 4 cosine theta puts you along this line here. 0 keeps you at the origin. So that entire region is described in this way. So it's not a polar rectangle, it's something a little more general, polar region. So the theta is bounded by constants, but the r's are bounded by f of thetas. And that's a pretty good idea, pretty nice idea. It gets you some a nice extension of how to apply these polar coordinates to integrals over slightly more general regions. So 126, 130. Same thing. Yeah, express in polar coordinates this region here. Well, this is r from 3 to 5 and theta from pi over 4 to pi over 4, 2 pi over 5 pi over 4. Right, so this is pi over 4 less than or equal to theta less than or equal to 5 pi over 4, and r is between 3 and 5. Right, that's that polar rectangle. Right, r is between 3 and 5, and theta just goes from this line to that line, which is a slope of 1. Slope of 1 is angle pi over 4. 45 degrees. So that's 131. Where are we? I'm looking at the wrong chapter. 134. 134. All right, so for the following exercises, evaluate the double integral of f of x over r dA over the polar rectangular region D. So that should various typos in this book. That should be a D down here. So it says double integral over r. They mean r for polar rectangle. So either this needs to be a D or that needs to be an r. Apparently they mean D, whatever. So in 134 we have the polar rectangle from 3 to 5 and 0 to 2 pi. So that's this picture all the way around, this whole annulus. So this ring, it's called an annulus. So it's the whole annulus from 0 to 2 pi, r from 3 to 5. So 134. So we've got circle of radius 3, circle of radius 5. That is awful. That is awful. Alright, so this is 3. Oh. That's 5. And we're doing the whole ring there. So 0 less than or equal to theta, less than or equal to 2 pi, and then r between 3 and 5. And we're looking at the double integral over, so it's d, x squared plus y squared dA. So that's the paraboloid. So that's the volume of the solid under the paraboloid z equals x squared plus y squared, and above this region D. So, you got that paraboloid there. And then you've got this annular region down here. So, I mean, this is actually pretty rough to draw. So it's this solid. It's an awful drawing, but anyway, I have to think about how to draw that nicely. So it's the double integral, okay, over. So we do the transfer to polar coordinates, transformation to polar coordinates. So you can do it in any order because these are constants, right? That's Fubini's theorem. When your boundaries are constants, you can just flip the dx and the dy or the dr and the d theta around. So I'll put the r in here, I guess. So that's from 3 to 5, and then from 0 to 2 pi. X squared plus y squared, what's that in r and theta? X squared plus y squared is just r squared, right? Remember the transformation. X is r cosine theta, y is r sine theta, and then x squared plus y squared is r squared. So this is r squared, and the dA, remember you have to have that, right? You have to have that little correction factor. So you're starting with a function in Cartesian coordinates, xy, rectangular, or Cartesian coordinates, and we're transforming it into polar coordinates. So when you transform from Cartesian to polar, the dA, it does not become dr d theta. Right? It becomes r dr d theta. And that had to do with how we set up the integral. Right? There's that correction factor there. So anyway, this is the double integral from 0 to 2 pi, 3, or the iterated integral, excuse me, r to the third dr d theta. So this is 1/4, 0 to 2 pi, r to the fourth, from 3 to 5 d theta. So 5 to the fourth is 625, minus 3 to the fourth is 81 d theta. So 625 minus 81 is 544. So 544. 625, 81, 4, 12 minus 8 is, no, 34. 5 minus, oh no, I don't have to, 12, yeah. 12 minus 8 is 4, 544. So 544 d theta, that's just a constant, so it just becomes 2 pi. So 1088 over, actually I'll divide by 2. So I have 544 pi over 2. Well, 544 is divisible by 2. It is 250 plus 22, 272. So 272 pi. All right. All right. So that was 134. Now one could actually do this in Cartesian coordinates, but it would be a pretty nasty calculation. One could do it, but I mean, describing the region, requires using, this business for a circle, you know, and then you would really only do the in the first quadrant. This thing is all nice and symmetric about the x-axis and the y-axis, so you could just do the integral in the first quadrant and then multiply by 4. But it's, that would be way more trouble than it's worth. All right. So 134, 138. So same thing, just calculate this in polar coordinates. So we've got r goes from 0 to 1, and then pi over 2 to pi. So this is this 1/8 of a circle. So ye old pizza slice. Oops, no. That's pi over 4. Sorry, it is not ye old pizza slice. It is ye old quarter of a pizza. So from pi over 4 to pi, or pi over 2 to pi, so that's that. So calculate, so that's d. And we want to calculate the double integral of the third root right? Third root x squared plus y squared. So we'll do theta first. No, let's not do theta first. Let's do r first. So r goes from 0 to 1, and then theta from pi over 2 to pi. And then x squared plus y squared is again r squared to the third, or 1/3. And then the dA is r dr d theta. So that's the double integral from 0 to 1, pi over 2 to pi. So r to the 2/3, dr, nope, r to the 2/3 plus 1. So it's r to the 5/3. 2/3 plus 3/3 is 5/3, dr d theta. So adding 1, it's 8/3. So that is 3/8 r to the 8/3 from r equals 0 to r equals 1 d theta. So the integral from pi over 2 to pi, so this just becomes 3/8. 3/8 d theta. That's a constant. So it's just 3/8 times the difference of these is pi over 2. So that's 3 pi over 16. All right, so the the problems in this section, oftentimes they're kind of easy because we use these polar coordinates to calculate things over regions that are somewhat circular. So you kind of only use it when it makes life easier. So that's why a lot of the ones in this section are sort of appropriate. So after 138, there's 140. Oh boy. Oh, okay. I see what they're doing with that. Yeah, that's silly. So the d is r goes from 1 to 2, theta from pi over 6 to pi over 3. So that's a really tiny region there. So pi over 6 to pi over 3. So that's 30 degrees to 60 degrees. And then r from 1 to 2. So it's just that right there. And so this is d. I mean, not that you have to draw the picture in these cases, but I'm just doing it for kicks. So we want to calculate the double integral over d, sine of arctangent y over x dA. So we'll do r again, I guess. The integral from 1 to 2, and then pi over 6 to pi over 3. So with the transformation to polar coordinates, again, x is r cosine theta, y is r sine theta, and then y over x is tangent theta. Right? It's r sine theta over r cosine theta, cancels r, and you just get tangent theta. Sine over cosine is tangent theta. So what does this become? It is sine of arctangent of tangent of theta r dr d theta. Well, r tangent of theta is just theta. So this is equal to the integral from pi over 6 to pi over 3 r sine of theta. Oops, I forgot the 0 to 1, or the 1 to 2. So r sine of theta dr d theta. Antiderivative with regard to r. So here we've actually got a theta going on there. So, but the antiderivative with regard to r, sine theta is constant, so it's just 1/2 r squared sine of theta from r equals 1 to r equals 2 d theta. So it's equal to the integral from pi over 6 to pi over 3. So 4 over 2 is 2. 2 minus 1/2, so it's 3/2 sine of theta d theta. Antiderivative sine is minus cosine from pi over 6 to pi over 3. So this is equal to minus 3/2. Pi over 3 is 1/2 minus root 3 over 2. So this becomes equal to root 3 minus 1 times 3. So 3 root 3 minus 3 times root 3 minus 1 over 4. Okay. Which is a positive number. All right, let's see if we got time for one more. 148, yes. 148. In the following exercises, convert to polar, then evaluate. So 0, 3, 0 to 9 minus y squared. X squared plus y squared dx dy. Right? Oops. Alrighty. So we need to look at what this region is. So this is a type 2 region. And it's 0 less than or equal to y less than or equal to 3. 0 less than or equal to x less than or equal to square root 9 minus y squared. Now, that's x equal to square root 9 minus y squared. That's part of the circle of radius 3, right? So, I mean, you can do this in rectangular coordinates, although, you don't really want to. It works out much nicer in polar coordinates, but let's draw it so we can see what we're dealing with here. So y goes from 0 to 3, and x equals positive square root 9 minus y squared. Well, that's the circle of radius 3 from 0 to 3. So there's 3, here's 3, and x goes from 0 to that. So x goes from here to here. All right, so this is x equals square root 9 minus y squared. It's also just x squared plus y squared equals 9. So this is a polar rectangle. So in polar, this is 0 less than or equal to r less than or equal to 3. 0 less than or equal to theta less than or equal to pi over 2. Very simple. Polar region. So we have a type 2 description. We have a polar description. Obviously, the polar description is a lot nicer. Well, actually, I mean, if you wanted to do this not using that, I mean, look, you're going to do dx. So you're going to do 1/3 x to the third dx right here for your antiderivative. And then plug in that. So you're going to have 9 minus y squared to the 3/2 power. Okay, and that needs a trigonometric substitution to do the integral with regard to y. Right, so that would require a trig substitution, this one here. So, I mean, obviously we're getting away with something here and saving some work. So this original integral right, this is your d. So this is just the double integral over d, x squared plus, I mean, if you don't need to do this step, I'm just going to write it out. Now I'm going to transform that to polar coordinates. So 0 to 3 for r, 0 to pi over 2. X squared plus y squared is just r squared. dA is r dr d theta. So 1/3 r to the third. From r equals 0 to r equals 3. So that's, well, 3 to the third over 3, so that's just 9. So 9 d theta, that's just a constant. So it's 9 times the difference of these two, so it's 9 pi over 2. Okay, so, oh wait. No, I'm sorry. This was r to the third. I did that wrong. dr d theta, antiderivative is 1/4 r to the fourth. So that's 81 over 4. Anyway, so that's 81 over 4 times pi over 2. So it's 81 over 8. 81 pi over 8. Right? I mean, if just to add in just that little bit of work there, this is 81 over 4, pi over 2 minus 0, so 81 pi over 8. All right, let's see if we can't get one more in here. 155. So evaluate double integral over d, r dA, where d is the region bounded by the four-leaf rows. R is sine 2 theta. Okay, so the four-leaf rows r equals sine 2 theta. At theta equal to 0, r is 0. In the next place it hits 0 is at theta equal to pi over 2. 2 pi over 2 is pi. And then at pi over 4, we're out here. So let me draw that for you. So the four-leaf rows. So this is pi over 4 equals theta. So we're looking at r is sine 2 theta. So this is r equal to 0 for theta equal to 0. And then as theta goes out to pi over 4, 2 theta goes to pi over 2. So that goes out to 1. So that's the point 1 comma pi over 4. And then as you go another pi over 4, you get back to 0. So this is, right, so theta is going out to pi over 4, and then theta is coming from pi over 4 to pi over 2. Gives you one turn of that leaf, of the four-leaf rows. So this is 0 less than or equal to theta less than or equal to pi over 2. And then r goes from 0 to the sine 2 theta. Now, when your r doesn't have constant bounds, you have to do theta first and then r. So r bounded by constants, theta bounded by constants, and then r bounded by functions of theta. Right? So constant bounds, theta bounds. So double integral over d of r dA. Oh, sorry. No. Wait. 155. Oh, that's 154. Crud. Oh, find the total area. This is the 154. But wait a minute, you can't double integral of r dA. Well, I guess you can do that. I mean, normally you would say the double integral over d of like x dA or something like that. So in 155, find the, let's forget about that. Find the total area of the petal, right? So the area of the petal, the area of D is the double integral over D of 1 dA. So that's the integral from 0 to sine 2 theta, and then 0 to pi over 2 r dr d theta. All right, so the antiderivative with regard to r is 1/2 r squared from 0 to sine 2 theta d theta. So at 0 you get 0, and that, well, not negative. And then at sine you get just sine squared 2 theta. So to do this antiderivative, you need to use the half angle or double angle formula, or whatever you call it. So this becomes 1/4 1 minus cosine 4 theta. I don't know if you remember that double angle formula there. Right, double angle formula was sine squared x is 1/2 1 minus cosine 2x, and cosine squared x is 1/2 1 plus cosine 2x. So double angle formulas or half angle formulas, whatever you want to call them. So antiderivative with regard to theta, so that's equal to 1/4 theta minus 1/4 sine 4 theta from 0 to pi over 2. So at pi over 2, you get pi over 2 minus 1, well, sine 2 theta, sine 2 pi, right? 1/4, well, it's just 0. Sine 2 pi is 0, right? Pi over 2 times 4 is 2 pi, that's 0. Minus evaluating at 0, well, that's 0, and then sine of 0 is 0. So you just get that. So it's pi over 8. All right, so that's the area of that one petal of the 4-leaf rose. Okay, so just a few more problems here in section 5.3, 156, 166. So we'll take a look at those next time. Start with those, and then we'll move on to the next section. The section on triple integrals, section 5.4. Probably we'll be able to do 5.6, maybe 5.5 or 5.5. I mean, cylindrical. Well, some of it. We'll see. I'll think about when the exam can be. I think tentatively 2 weeks from now is. Let me think about it. Okay, so that's all for tonight. Have a good weekend, guys. Send me